What was the central thing about Hawking?
Well, I think the public saw him as a messenger from the stars.
I can't take it seriously.
But I have to admit that I was wrong.
All hell broke loose in the physics community.
Embark on a cosmic odyssey as we dive into the captivating mysteries of black holes, cosmological enigmas that have fascinated scientists for decades. In this video, as we'll unravel 10 compelling theories, unlocking the secrets that lie beyond the event horizons. Prepare to be immersed in the mesmerizing intrigue of a black hole's inner realm. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space, and beyond, consider subscribing. Stephen Hawking made an error. In the field of cosmology, Stephen Hawking stands out as a significant figure, second only to Einstein. Widely recognized as an icon in modern physics, his groundbreaking contributions transformed our comprehension of the universe, particularly in unraveling the enigmas surrounding black holes. Being an eminent scientist entails not just unwavering accuracy, but also the capacity to acknowledge and rectify errors. Stephen Hawking, a key player in advancing our understanding of black holes, was not immune to occasional mistakes. The intricate nature of black holes, defying conventional physics, presents a formidable challenge in achieving precise calculations, resulting in occasional deviations. Since the 1970s, Dr. Hawking maintained that black holes represented intense concentrations of gravity formed by spent stars, consuming matter and energy irreversibly, leaving behind only an unrecognizable burst of heat. However, at the 17th International Conference on General Relativity and Gravitation in Dublin in 2004, he graciously admitted to his earlier misconception, a fundamental question in theoretical physics persisting since Hawking's revelation of black holes emitting thermal radiation in 1974, revolved around whether information is lost during black hole evaporation. In 2004, Hawking asserted that he had resolved this long-standing inquiry, acknowledging his earlier error. His revised understanding underscored that information about matter engulfed by a black hole is not genuinely lost. In contrast to previous beliefs, quantum effects cause a black hole to radiate steadily, challenging the idea of a black hole as an eternal cosmic entity. Instead, Hawking proposed that a black hole ultimately disintegrates, releasing matter and energy in a distorted manner. Black holes. Not all black holes look like the usual idea of a completely dark, empty sphere in space. Some might think of it as a huge vacuum, like in cartoons, sucking everything in. But it's important to know that black holes can look different, and they aren't always completely dark. Contrary to what many think, light can still come from the area around a black hole, even beyond its edge. Some black holes are very bright and are called quasars. These are supermassive black holes at the centers of faraway galaxies, and they get their brightness from consuming a lot of gas. Quasars are often formed when two galaxies crash into each other and a lot of gas falls into the black hole. As the gas goes towards the black hole, it gets really hot and gives off light across the whole spectrum. This brightness is so strong that it lights up the entire galaxy, making it way brighter than what we might expect from a dark black hole. Also, the color of a black hole might not always be black. This happens because of how gravity near a black hole messes with time. This makes things heading towards the black hole look like they're not moving from far away. For example, a spaceship going straight into a black hole might look like it's not moving to someone watching from a distance, even though it's getting closer. Similarly, a light source that's getting pulled by a black hole could seem like it's floating in space forever. This bright object would keep getting redder and fainter until it would eventually disappear. Scientists call this redshifting, universe's vacuum cleaner. On the surface, black holes might appear to function like cosmic vacuum cleaners. As singularities, they embody a concentration of nothing but immensely gravitational force, powerful enough to warp space and time in their vicinity. However, it's crucial to clarify that they don't act as giant vacuum cleaners, indiscriminately sucking up everything in their path. Despite their extreme characteristics, black holes lack infinite mass. Their gravitational influence is constrained by the specific mass each black hole possesses. For instance, stellar black holes, formed from massive stars, only carry the mass equivalent to that particular star. Consequently, similar to how objects can orbit around a massive star without being drawn toward its center, objects can perpetually orbit around a stellar black hole without succumbing to its gravitational pull. Nevertheless, caution is still warranted when approaching a black hole. The dynamics change dramatically in close proximity, and the consequences would be vastly different from a safe orbital distance. Not a hole. Certainly, black holes are not holes after all. As mentioned earlier, black holes shouldn't be likened to empty spaces or portals as illustrated in Looney Tunes, embedded in the fabric of space-time. Instead, they represent a spatial domain where time and space take on strange and unfathomable qualities. The mystery beyond the event horizon remains elusive, and at present there's no feasible method to unravel this puzzle. However, some scientists still contemplate the idea that certain black holes might act as conduits to other areas in the universe, commonly known as wormholes. They like to move it. Initially, when black holes were uncovered, there was a prevailing belief that they served as fixed points in space-time, inexorably drawing nearby matter and energy towards their ultimate demise. However, observations have shown that they don't perpetually attract everything, and similarly, they don't prefer to remain stationary. Much like galaxies, stars, planets, and all celestial entities, black holes exhibit a penchant for traversing the universe. This mobility becomes particularly evident when two black holes collide or merge. The revelation of their dynamic nature came to light when the first gravitational wave was detected in 2015, a consequence of the collision and subsequent merger of two black holes. Not all the stars become black hole. There was a widespread belief that all stars concluded their life cycle by becoming black holes, but astronomers dispelled this notion long ago. While stellar black holes indeed form when massive stars deplete their fuel and undergo a cataclysmic collapse, this fate is not predetermined for every star. For instance, stars like our Sun or those of a similar size are more likely to culminate their existence as white dwarfs. Even more massive stars don't necessarily become black holes. If the star's core withstands gravitational collapse, it may transform into a neutron star. It is generally thought that a star needs to be at least 20 times the mass of the Sun to approach the possibility of evolving into a stellar black hole. Furthermore, the origins of supermassive black holes are still under exploration, and it remains uncertain whether they are formed from stars or through alternative mechanisms. No spaghettification at the event horizon. The intense gravity of a black hole is so powerful that it warps time, causing any object falling into it to appear spaghettified when viewed from a safe distance. Spaghettification refers to the stretching effect that amplifies until the object is eventually torn into a string of individual atoms. Commonly, researchers have assumed that spaghettification invariably occurs at the event horizon of a black hole. However, this is not universally true. While spaghettification is indeed a real phenomenon associated with black holes, its precise location can vary depending on the size of the black hole. For instance, in the case of supermassive black holes, this phenomenon occurs much later after passing the event horizon. Enter black hole. While it is an undeniable truth that the overwhelming gravitational force of a black hole would be unsurvivable, surprisingly, this force wouldn't be the cause of your demise if you were to fall into a black hole. Instead, it's the phenomenon known as spaghettification that would lead to your disintegration before gravity could compress your insides. As discussed earlier, spaghettification involves the stretching effect that amplifies until the object is torn into individual molecules. So even before reaching close proximity to the black hole, where its immense gravity could compress you, the process of amplification would rip you apart into molecular fragments. This disintegration would occur long before you could sense the weight of the entire universe crushing you in your final moments. We can see them, although it is a well-established fact that light cannot escape once it has crossed the event horizon due to the nearly infinite strength of gravity within a black hole. This does not render black holes invisible. We can still study and observe them by examining the movement of stars in their vicinity. The initial detection of Sagittarius A utilized this method. Moreover, advancements in technology now enable us to capture photographs of black holes, as exemplified by Sagittarius A. Telescopes play a crucial role in this observation, identifying black holes by detecting the expansive accretion disk composed of stars, gas, and other materials spiraling towards the center, similar to the case of the M87 supermassive black hole. The material within the accretion disk undergoes heating through friction as it swirls at near-light speeds, leading to the emission of electromagnetic radiation, which serves as a key indicator for the presence and characteristics of black holes. We can make one. Since the inception of the Large Hadron Collider, LHC, the world's largest particle accelerator, there have been widespread rumors and concerns among the general public and certain segments of the scientific community. The apprehension centered on the notion that the powerful particle collisions within the accelerator could potentially create minuscule black holes, posing a catastrophic threat to humanity. However, the scientists at the LHC, acclaimed for confirming the existence of the Higgs boson particle, effectively dispelled these fears. They demonstrated that the particle collisions induced at the LHC are fundamentally similar to those occurring naturally on Earth. The accelerator merely facilitates these collisions in isolation, providing physicists with a controlled environment for observation and study. Furthermore, even if we could aggregate the mass of every object in our solar system, it would still be insufficient to generate a stellar black hole. Concerns about the LHC producing microscopic black holes also arose, although even cosmologists remain uncertain about their actual existence. So the question remains, do tiny black holes truly exist in the universe?